Okay, this is Physics 1C for March 4th. Today we're going to continue to talk about Gauss's law and look at some of the applications of it, and then talk about the effect that some things we can learn about how conductors behave because of what we know about Gauss's law. So just a brief review of what we did last time. We developed the idea of electric flux, and the symbol that we use for electric flux is this, phi sub E. And we said that Gauss's law tells us that when you calculate the flux through a closed surface, any closed surface, that the total flux through that surface is always equal to the charge that's enclosed within the surface divided by epsilon naught. This is kind of running off the screen a little bit, isn't it? So I'll move this over. So that's what we learned last time. And we're going to apply that to a plane of charge. And then we're going to talk about conductors in equilibrium. And then we're going to apply it to kind of a concentric spheres of charge, which is something you're going to see show up on your homework in a couple problems. So let's get started. So plane of charge, it says find the electric field due to an infinite plane of positive charge with uniform surface charge density sigma. So an infinite plane is something, I guess the way we'll look at this is we'll just draw like a kind of a plane that we're looking at edge on. So it'll look something like, oops, maybe like that. And this plane is going to go on forever, but I'll just kind of draw a slice of it. So like that. So this plane is covered in positive charges. The charges have, it says uniform, that's going to be important, surface charge density sigma. That means sigma represents the amount of charge divided by a unit area within the system. So we've got positive charges all spread throughout this object, like this. And then the object kind of continues on in all directions, so it's an infinite sheet. You might wonder, why do we talk about infinite sheets? That's kind of silly. But in reality, the idea here is that the result we get can be extended to really any piece of metal that has charges on it, as long as you're close enough to it. Okay. So the first thing we do when we try to solve these type of problems is we need to draw electric field lines. And for an infinite plane of charge, I would argue that the field lines are going to look, let's make them green, something like this. They're all going to point parallel to one another and out away from the surface of the object, kind of like that. And then we'll just duplicate these. Oh, I can't copy paste them. We'll just paste a few of these and just kind of drag them down like this. Oops. Should be enough. And then do the same thing on the back. I'll try to make these look somewhat three-dimensional, but I'm not going to do the best job. Just like that. And like that. Okay, that looks okay-ish, I guess. So we've got electric field lines that look like this, and then those same electric field lines are going to point out the back. I'm not going to try my best to make these ones in the back as oh, I have to though, because I can't draw straight. Right. So on the back side, you're also going to have electric field lines. Maybe I won't draw as many, so we'll have like one. We'll just draw like 4 lines coming out the back. So basically, you can imagine that the electric field lines in this situation are just, they're all parallel to one another. They point in straight lines. Yeah. So our goal is to find the electric field of this kind of a system. And we're going to do so by using Gauss's law. And after drawing the electric field lines, what's the next step that I said last time we would do to solve this?
You pick a Gaussian surface.
Mm-hmm. Now we have to pick a Gaussian surface that is a good one, and a good one is one in which each piece of the surface is either perpendicular or parallel to the field lines, right? So we need a surface, and it somehow has to meet those kind of definitions. And it has to be a closed surface too. So what kind of surface could we use in this situation?
A cylinder.
A cylinder, okay. And then how are we going to shape the cylinder? Is it going to be shaped with the top end like up here? And then we draw the lines down just like we did with
But perpendicular to its axis.
perpendicular to its axis. You want to rotate it so that the circular end would be over here, then you're saying?
Yeah.
Okay, let's try that. How big do I need to make it? Do I need to make it infinitely long?
No.
A box would work too, Dahao. Yes. Yes, it would, as you will see as we do this. A cylinder, a box, anything as long as... Let me make this just a little bit wider. As long as the surfaces on this side and this side make it so that the electric field lines kind of cross them at a right angle, it'll work. So yeah, a box would work. Let's see how close to straight I got this. That's pretty close. So that's going to be our cylinder. And I guess for making things like look more three-dimensional, I guess, I'll do something like this to indicate that that's kind of the back side. And then this over here is the front of the cylinder. Okay, we need to include some dimensions for our cylinder now. So let's say that it has a length in this direction that's L. So that's going to be the length from here out to here. Let's say that the area of the end cap on this side is A, and so it's a right circular cylinder, so both of these areas will be A. Okay, so that's a good choice because now it should be pretty clear that all of the field lines on this side are pointing out to the right, and if we come along our surface right here and we pick a piece and we draw, oh man, drawing straight lines, struggle today. That would be our dA vector on this side. On the opposite side, we'd have a dA vector that would basically point out like that. And again, this is just a vector that represents the direction that the surface points at that location. On the curvy surface, then we're going to have, at least on the top side over here, the dA is going to point this way, which means it's going to make a right angle with the electric field lines. Same thing down here. And all over the surface of the curvy portion of this, the dA vector will point perpendicular to the electric field lines. Now we need to use this equation. And before I do, does anyone have any questions? And Dahao, do you see how if you just change this circle on the end here to a square and then just put a cube in, it worked just fine too, right? Cool. Okay. This is often called a pillbox. They always like to call it a pillbox in older textbooks. Okay, so I think we're good there. So we just go ahead and apply this equation. So our equation says that we need to do the flux over the whole surface. What I'll do is similar to I think it was the very last problem we did, we're going to find the flux through the curved portion. We'll find the flux through the left side, like the left end cap, and then we'll do the flux through the right side, and we'll just add them all up together to get the total flux. So the flux through the curved portion, we're doing integral of E dot dA, but we'll just skip one step here. We'll write that's going to become E times dA multiplied by the cosine of the angle between the electric fields and the dA vector. So for example, right here you can see that on the curved portion of the surface, that angle is going to be equal to what? It's going to be 90 degrees, right? Because the electric field line is going this way. The dA vector points perpendicular and away from the surface. So there's a right angle that's made right there. Another way to say it would be that the field lines are basically parallel to the surface itself at all those points. They don't actually cut through the surface. So you end up putting cosine 90 here. Is that clear enough? Can everyone see that? I noticed something I did wrong here too. Don't need that circle anymore. That portion, is that part clear?
Hmm.
Okay. So tell me what I write down for the left side. So we go integral. We're going to do EDA. And then what's the angle going to be now? The angle
0.
is 0, yeah. And it's important to understand that in this case, on both sides, the electric field lines always point away from the surface. So that means that on this side the angle is 0, and on this side the angle is 0. You might think on one side it might be 180 or something, but they're all parallel. Okay, so then that is going to become just... So now here's the next part that we have to ask. What do we know about this electric field if we look at this end cap right here? We're at a fixed distance away from the surface. So it probably seems reasonable to say that there's not going to be any difference in the electric field up here versus the electric field down here versus over here, for example. If it truly is infinitely long, then all of those points should have the same electric field. And that means that we can pull the electric field out of the equation, and now we just need to integrate dA, but now we're just integrating over this surface on the right-hand side. Whoops, we're doing left first. We're going to get the same answer both, sorry. On the left-hand side, we're just integrating over just this surface, the end cap. So when we do that integral over that left surface, you could even kind of indicate that it's the integral over the left cap if you wanted to down here. Then this is just going to give us E times A, where A in this case just represents the area of that end cap over there. And by the same arguments, you do all of the exact same stuff, but you do it over the right cap. And because our surface is just a circle, and the areas are the same, you get the same answer for both of them. Okay, so we need the flux through the total surface, the net flux, and that's going to be equal to, obviously, this symbol. However, we don't need to calculate this now because we've already done it. This is just going to be equal to the sum of 0 plus EA, right? So the total will be what?
Just 2EA.
Yep. And then the right-hand side of this equation is the part we have to worry about now, which is Q enclosed divided by epsilon naught. And so now we have to think about what is Q enclosed. And Q enclosed represents the amount of charge that's contained within our Gaussian surface. And how much is that going to be? How much charge of this whole big sheet is actually inside of our surface? The stuff out here is not, right? Above is not. What kind of cut out of this thing do we need to make to cover how much charge we've actually cut out? What kind of shape would it make on this surface here?
Circle.
A circle, yeah, exactly. Because if we project this piece to the left, we'll see that that's the kind of cutout we're going to get from our Gaussian surface. It's only going to be the charges contained within that little circle right there, right? So how much charge is contained inside that little circle?
Yes, sigma, and in this case, pi r squared.
Yeah, but we didn't label the radius of this for a reason that'll be pretty clear in a second, although you could put
It's
that
just sigma times the area.
Sigma times the area, exactly. So we get this equation. The left-hand side of Gauss's law reduces down to 2EA. The right-hand side of Gauss's law reduces down to just the charge per unit area times the area that we've enclosed here. And then, yeah, divide by epsilon naught. And then what always happens in these problems, it has to happen, is that the shape of your Gaussian surface can't possibly have an effect on this. It goes away. The area here goes away. That tells us that it does not matter how big we make it. You'll notice we never used the length. That did not come into play. This thing could have been as big as we wanted to. It doesn't really matter. And the area that we did end up using in the equation, it just disappears from our final result. And what we end up getting is that the electric fields, due to an infinite plane of charge, is roughly uniform near the surface, and it's equal to sigma divided by 2 epsilon naught. Look at that. believe we did this, we did a problem where we started with a disk of charge, and then we looked at the solution when you're some distance r away. But then we said, well, what happens? Actually, I think it was called X. We said, what happens when we make this thing infinitely large? And it turns out that you get this result right here. And it's kind of interesting because it tells us that it doesn't actually matter how far away you are. You still get the same answer. That's kind of weird, right? Why is there no distance showing up here? Why didn't like L over 2 show up, the distance that we are away? How come that didn't show up in this result? Can anyone come up with an argument as to why it doesn't matter how far away you are?
Is it because no matter how far away you are, the projection on that plane is going to be the same? It's just going to be the circle?
I would say no, because that's what you're saying is that the projection would be the same, but we could have chosen any shape we wanted to, right? The Gaussian surface is more like a what's a good word for it? I mean, it's just a tool to get you to a solution. So the fact that this solution doesn't vary when you get farther away, the Gaussian surface itself doesn't have anything to do with it. Anyone else want to try? Why does it not matter how far away you are?
I was thinking about the electric field lines because they're just going straight.
Okay.
So, and there's no they're not tapering off, or they're not their density, so to say, is not changing.
Yeah, their density is uniform. The distance between adjacent lines, basically, you're saying?
Yes, yeah.
Can anyone come up with a more like geometrical reason? The only problem I have with your explanation, Cam, is that it assumes the solution in a way. Like, yeah, the electric field lines are evenly spaced because I know that it's constant, right? That's all I'm saying. How can it be that if you're really far away from this thing or if you're really close to it, you still get the same answer? What is it about the geometry of this problem that makes that work?
Is it because they're parallel? Or?
No, I don't think so. Again, they're parallel because it's uniform. So you got to come up with.
I mean, it's an infinite plane.
Interesting. Yes, it is, right?
So.
Yeah, I was going to say it does go on forever, so it shouldn't really matter where you are, right?
Yeah, so this plane basically that's basically the right answer, yeah. And one of the persons typing, I don't know if that's what you were going to type, but yeah, like there's other ways to say this, so this isn't the only answer, but this object looks infinitely big no matter where you are, right? Doesn't matter. I mean, you get really far away from it, it's apparently still just an infinitely big sheet, right? So yeah, what this is saying is that, because it's infinitely big, whatever perspective you look at it from, it's still infinitely big, right? Now, the reality is that there are no true infinite sheets, right? So when do you use this? Well, reality is we kind of say that this is the solution you get when you're close to a plane. So let's say you've got a plane of charge right here, like this, and you go some tiny distance above it or something like that, and you want to know what the electric field is there. We say this is the solution when you're really close to that plane so that it looks like it's infinitely big, basically. All right. So that's the last of the kind of like basic Gauss's law examples that you'll see show up in every single textbook. Those are the sphere of charge, the cylinder of charge, or the line of charge, and then the plane of charge, right? Every single textbook. We'll do one more here in a little bit, but first we're going to talk about conductors in equilibrium. So let's do that. So that we're going to do this problem here. I don't know if you started doing the homework yet. You probably, if you have, you've probably seen a figure that looks something like this. Okay, so the next thing we want to talk about are conductors in electrostatic equilibrium. Okay, conductors that have charges that are basically not moving around. What are their properties like? So this is a list of all the properties. I didn't really feel like writing every one of these long sentences out. Instead, what we'll do is we'll go through and we're going to prove each one of these. So we'll take our time to go one by one through these. So the first one says, the electric field is 0 everywhere inside the conductor, whether the conductor is solid or hollow. Okay, so what does that mean? So suppose that we have some conductor, okay? And we'll start off with just like a simple conductor. What is a conductor? It's like a piece of metal, right? So we have some kind of a metal sphere. Doesn't matter what type of metal it is, just some kind of a metal sphere. And what this says is the electric field is 0 everywhere inside the conductor, right? So the idea is that inside of here, the electric field is 0. So why would that be the case? Now, there's a few different ways to prove this, but one way to do so is to say that suppose that it weren't the case, right? Suppose that it weren't the case, that the electric field is 0. Suppose that we try to make the assumption that the electric field inside of the conductor is not 0. What would happen? So to understand this, let's place some charges in here. Let's say you have some excess charge within this system. Let's say that we try to place another charge in here, okay? And let's say we make the assumption that our electric field inside of this object points this way. Let's say that we just assume that there's a possibility that there's an electric field that points to the right. So if there was, then if I were to place another positive charge inside of here, what direction would the force on that charge be?
It would be towards the right.
Yeah, I'd feel a force this way. And if I placed another charge, for example, down here, due to that electric field, it would point this way. If I put a negative charge in here, let's use blue for negative. If I put a negative charge in here, it would feel a force that would pull it this way, basically, right?
Mm.
Okay. So we're talking about conductors in equilibrium, okay? So if you do, in fact, have some kind of a field in here, you're going to have this effect that free charges within the metal are going to tend to want to pile up on one side, right? Positive charges would go to the right, negative charges would go to the left, right? Does that make sense? So it would kind of violate this word, equilibrium, right? Because then you'd have charges that were moving, basically, and it would no longer be in equilibrium. So that tends to kind of make things kind of break. But we can go a step farther, and we can say, let's look at another type of a system. What if I just take a piece of metal, we'll use black again, like a slab, like this, and let's say that instead of talking about a field on the inside, right, let's say that we place an external electric field on the system. So we say there's a field, an electric field, external, so we're going to call this, why did that come up? I don't want that. We're going to call this the external electric field. So say you have a piece of metal and you apply an external electric field to it, right? So we've got an external electric field, and let's say that it just goes like this. It goes straight through our object. And how would you do this? Well, I mean, you could just use what we said a second ago, which is that if I put a positive plate over here, I put a negative plate over here, then it's gonna have this effect. So I've got this electric field that's external to my metal, right? What is that going to do to the electrons within this system? So if I'm an electron and I'm sitting in here, a little negative charge, what direction is the force on that going to be? And keep in mind that this external electric field goes straight through the system here. But I'm putting dashed lines here for a reason you'll see in a second.
It'll be towards the left.
It'll be towards the left. So this negative charge is basically going to move as far as it can, which it can't really escape the metal, okay? It's just going to move to the left. And any other free electrons within this, which, you know, there's a lot of them because it's a metal, and each atom within the metal may contribute 1 to electrons each. So you can imagine there's just a bunch of electrons, right? So these free electrons are then going to all tend to basically pile up over here on the left side, right? Like this. And any free electrons in the middle, they can't help themselves. They basically just have to move to the left. What that's going to do is it's going to leave basically a kind of a excess positive charge over here on the right side, as those negative charges are basically just going to be pushed as far as they can away from these, right? But now what happens that's interesting is you end up with a bunch of negative charges piling up on the left side and a bunch of positive charges piling up on the right side. And you'd ask, well, how long is this process going to occur? Are an infinite number of electrons just going to pile up on the left side? And the answer is no, because something else happens as this process is occurring. When you have a bunch of positive charges that are piled up over here and a bunch of negative charges that are piled up over here, then it's almost like you have a sheet of positive charge on one side and a sheet of negative charge on the other side, right? So as a result, there's basically an internal field that gets set up like this. And as you can see, that internal field that I'm drawing, because it goes from positive to negative, is opposite to the external field, right? So once all the charges have started moving and the system reaches equilibrium, that's what we're talking about here, equilibrium, what ends up happening is that the sum of these two fields on the inside will be equal to 0. Because that's the point, right, when the charges will stop moving, is when the total electric field is 0. This is exactly like what I'm teaching in my 1A class right now, because in 1A we're talking about equilibrium. In physics 1A, what do you have to have for equilibrium in physics 1A?
Net force is 0.
Net force is 0. Well, this is the same idea if you just multiply by charge, right? Because Q times E is force, right? So the net force on all the charges inside is 0, and as a result, the electric field inside ends up being 0. So that's just how it works. Anytime you have a conductor, whether it's free, like this one, with no external field, or you apply an external field, it always works itself out so that the field inside automatically drops to 0. The electric field is 0 everywhere inside the conductor. Whether the conductor is solid or hollow, what does that mean? Well, that means that I don't know if this is confusing here, but we made this assumption that the electric field was not 0, and it led to kind of a contradiction, because it would imply that if it wasn't 0, the charges would be moving, so it wouldn't be in equilibrium. So in reality, the field inside of here is also 0. Okay. Oh, solid or hollow, what does that mean? So hollow would mean, suppose that I have a shell, and this will be one of the things we do in the next problem. Suppose I have a metal shell, like this. Okay. The idea here would be that the electric field would be 0 inside of the shell itself, but it would also be 0 in the kind of cavity, so to speak. They always call these cavities. Does that make sense? Think of what is a metal shell? Think of like a tennis ball, because they're like hollow on the inside, right? But instead of being a tennis ball, just replace it with a piece of metal, basically. All right. Any questions?
Okay, so it's like, so when it's in that state, is it possible to like cut the metal down the middle and then turn off the external electric field? And then there will just be like an induced electric field between the plates?
No. So if we were to turn this guy off, the external field, right? what would happen is that all of these negative charges would now be free to basically go and annihilate with their positive charge partners, right? And that's what would happen. These negative charges would then basically fling them back over to here until you got back to the case where the electric field inside is 0. So basically, put another way, if this becomes 0, then this also has to become 0. Does that answer your question?
So, but like you can maybe somehow separate them. Like maybe if the metal was like,
Oh, do you
maybe
mean
it was
do you
like
mean
two
do you mean
pieces of metal.
do you mean if you basically came along here and you basically just cut the metal down the middle? Is that what you're saying?
Yeah.
I do think you could use that as a way probably to get a negatively charged metal and a positively charged metal, probably. As long as you did it while the field was on. Is that what you're saying?
Yeah.
I think that would probably work. Yeah. I know that it should work because I'll give you another example that's maybe a little bit easier to understand. Suppose that I have a insulating stand, okay? And on this insulating stand I have a neutral sphere, okay? And right next to this, touching it, I place another neutral sphere, okay? Also standing on its own stand that can be moved, okay? Which if you're in the classroom, I could just show you this because we can do this experiment in the lab. So I've got two metal spheres that are touching, right? So just to make the process simpler, what we do now is we say, suppose that I were to come along here and I take a plastic rod that is a negatively charged plastic rod, and I bring it really close to this sphere on the left, okay? But a little bit farther away from the one on the right. So negatively charged rod gets brought close to this. The effect of that is going to be that the negative charges are going to tend to pile up as far as they can over here. Positive charges are going to tend to pile up over here as far as they can, right? Literally the exact same thing is what happens in this process, right? Because this rod acts as your external field, right? And now what you can do is you can simply just separate the objects from each other, right? So you leave the first one in place, right? You leave your rod right here. But while the rod is still close by, you move the other object away. And now what's going to happen is these negative charges are going to redistribute themselves all along the outside edge. If you read number 2, you'll see that's one of the things that happens. And now you pull this away, so you get rid of your negatively charged object, right? And then lo and behold, you have basically a positive and a negatively charged sphere. And in addition, you can probably guess that they'll have equal charges too. Like if they started neutral and you did this process, then these should end up with equal charges, right? So now you've got some positive Q over here and some negative Q over here. That's kind of the same experiment that you're talking about, right? But we don't need to, cut a piece of metal in half. Right? Yeah.
I guess you could keep doing it over and over with like a stronger external field,
Yeah.
and then just get stronger and stronger charge.
Yeah, absolutely. So this is a type of, it's kind of similar to charging by induction because you didn't actually rub. I don't know if I made this clear. You don't touch this to this. You're just getting it close by. It's not conduction because you're not rubbing like these pieces of metal with something to get extra electrons onto them or something like that. You're just bringing something nearby that forces them to move around and then separating them. But yeah, you could continue this process over and over and over again to get more and more negative charge on something if you want to, or more and more positive, right? Because you could now take this positively charged object. You could, yeah. But anyway.
Is there a way to tell if one sphere is positive and the other is negative?
There is. So we use something called electroscopes to do this, and I showed a little video of it, but just to describe what electroscope is. So an electroscope is a device where you have kind of a container that is insulated on the outside. So it may be made of like plastic or something like that. And then on the top, what you have is like a stopper. And attached to that, you have usually something like a metal ball, but it could also be like a metal sheet. So some kind of piece of metal here at the top. And then connected to that metal is a piece of wire here. And that wire basically extends down to here. So you have, like a wire, it's more like a rod usually. And then hanging off this rod right here, you have two pieces of metal. Commonly, they will use like gold leaf because it's I don't know why they use gold leaf, but they do. You have two little pieces of metal that hang down like this, And what they'll do is normally they'll basically just be hanging. But then if you bring, for example, a negatively charged object nearby this ball, so usually what we do in the lab is you just take a piece of plastic and you rub it with rabbit fur, and then you bring the negative charge up here. Again, we saw this in a video. What happens to these leaves on the bottom when you bring a negatively charged object up here?
Start wiggling around.
Yeah, they spread apart. Like this would go this way and this one would go this way. Okay? And that occurs because negative electrons that are inside of the ball up here basically rush down to the end of these leaves, which is as far as they can go, because this is like an air container. There's just air inside of here. So the electrons go as far as they can, which is basically down here, and this ends up being negatively charged, this ends up being negatively charged, and they repel each other, right? Now, we could have done the same thing with a positively charged object, and you'd probably guess that exactly the same thing would happen, right? But instead of negative charges down here, we'd have positive charges, right? So that doesn't really answer your question, right, Cam, of how do we know if it's positive or negative? So what you can do is you can basically like bring the negatively charged object nearby. You can have it charge up these leaves with negative charges like this right here, right? And then what you do, and this part I don't know if I can draw this very well, you basically touch the ball with your hand. Okay, so your finger comes up here and just touches the ball. I'm just gonna draw one finger. I don't want to draw a hand. It's gonna get ugly. So you touch the ball with your finger, and the effect is that the ball basically... Here, let's draw a person. That's a person's arm. Okay. This person's touching the ground, right? So they touch the ball, and what ends up happening is that all of these electrons, right, are going to now have a new path. They can now go through the person. Let's use the same color. They can basically go through the person and all the way back down into the earth, into the ground. This is usually the symbol that's used. What's the symbol for ground? It's like this, right? Yeah. So that's the symbol for ground. So they basically go straight into the earth, straight into the ground, all those negative charges. But then what you do, okay, next step is, I have to redraw this. Now what you do is, while your finger is still touching it, no. Yeah. Next step is remove your finger and then remove the rod. And as a result, what's going to happen to the charges on these leaves?
They would have traveled through your body back to the earth, so they're going to lose the charge.
They're going to lose the negative charge. So what charge are we going to have on these guys now?
It's going to be positive.
Yeah, positive. So the way this works in reality is that when you touch the ball, the leaves fall back down to flat like this. And then when you let go and then move this away, they flat back out like this, okay? And now you actually have your proper electroscope. We call this an electroscope.
Oh, okay.
Because now we know it's positive. We know for a fact it's positive. Now we had to use some assumptions. Like for example, you need to start with a reference, right? You need to have something that you know is a negatively charged object, but that's not a problem because we know that when you rub plastic on fur, you get a negative charge. And there's a lot of studies that have been done on this. Like you can go read about something called the triboelectric series if you want to. But there's things that tend to become more negative and things that tend to become more positive when you rub one surface on another. And there's like a little chart basically. It's kind of an ordered chart, so it's like when you rub silk on glass, you get positive on the glass, and if you rub mica on, I don't know, plastic, you'll get something else. Anyway, point is now this thing can actually measure charges because what'll happen is if I bring a positively charged rod over here, so I take a piece of glass and I charge it positively, what's going to happen to these two leaves now when I bring a positively charged object really close to the metal ball at the top?
Oh, they're just going to spread wider.
They're going to go farther apart, exactly, because now you're going to basically... There's one way you can think about it is you send more positive charges away from this guy, because they want to get away from it, and then they pile up down here, and it's going to spread out farther. And if I bring a negatively charged object, the leaves will close down. So you basically, now you have something that can test if something's positive or negative. So that's how you do it. This is a good question. Something we should have talked about earlier, and if we were in the lab... I would have shown you. I would have let you guys play with this stuff, but anyway. What's up?
Did we assume some... Okay, so did we start off with like some relative charge for in our first one with the blue stick, because we
We knew this was
defined that as negative.
We knew it was negative, yeah.
Okay.
Keep in mind that our definition of what's positive and what's negative, it doesn't really make any difference. What we had originally called positive, like we could have made it so that electrons were negative, or sorry, we could have made it so that electrons were positive and protons were negative, right? It wouldn't have. It doesn't physically change anything. Basically.
Oh yeah, okay.
All the rules still work basically. So at some point in time, someone had to make a choice, and I guess it's probably Franklin. Like Franklin is probably the reason why we have negative electrons, and because he was the first person to distinguish that there were two types. Before that, it was just electricity. You know, they understood static electricity; they could produce shocks, and they knew about lightning and stuff like that. But they didn't know that unlike fire, there's just one type of fire, right? There's not positive fire and negative fire. But for electricity, they called it the electric fire, and they didn't know. But then Franklin figured it out. And so, yeah. As long as you pick one, you can now measure everything else in the universe, right?
And by this you can.
And that's not that much different from anything else, right? Because in order to define mass, we have to have a reference kilogram, right? So it's the same concept. Sorry, I didn't mean to interrupt you. Go ahead.
Oh, so and then this is how you could find out that there are two different charges.
Yeah, it's really easy to prove with this. Exactly, 100%. That's right. Very good point. All right. Are you all ready to move on to number 2? So remember, number 1, these. Okay, I forget to do this. Why do we care about conductors in electrostatic equilibrium? Well, the reason we care is because they show up quite frequently, and the way that these conductors behave it's important for understanding certain things. And there's some really interesting things that come out of this, and I'll tell you one of them after number 2. About how you can protect yourself in a lightning storm. Okay. And maybe some of you already know the answer to that, how you can protect yourself in a lightning storm. Let's look at number 2. Number 2 says, if the conductor is isolated, that's important, and carries a charge, the charge resides on its surface. Okay? So this means that if a conductor actually has charges, that all those charges basically tend to move themselves to the surface. Now, I gave one argument as to why this would be the case before, which is, suppose you just start off with a couple of these and you want to put one or two inside of here. What happens is they're going to tend to spread themselves out as far as they possibly can from each other, right? And that means, well, they have to basically go to the surface, right? So that's one way you can think about it. But we can actually use Gauss's law to prove this one as well. So Gauss's law tells us that if we were to draw a Gaussian surface, for example, if I drew a Gaussian surface inside of here, and then if we said, let's suppose that number 2 is not true, and let's suppose that I actually managed to find a charge inside of here when I put my blue Gaussian surface in here, right? Then Gauss's law tells us that if there is some charge enclosed, right? Like if the charge enclosed by the blue little surface here is not equal to 0, then that means there's going to be an electric field inside, right? Does that make sense? If there's charge, there must be electric fields. So that's a complete violation of what we learned in the first part. We know the electric field has to be 0, so that means that this is not possible, which means that you can't possibly have any charges inside of here. And you can extend that idea all the way out to the surface by drawing Gaussian surfaces wherever you want within this surface here, right? But, yeah. So, if there's charges, the charge is going to go to the surface, basically. Okay? Does that make sense? So now you can actually apply this to the lightning storm thing that I was talking about. So most cars have a lot of metal in their frames, right? And if you're sitting inside of a car, you kind of have this like cage of metal that's around you, right? A guy named Michael Faraday figured out that if you have a metal cage, so let's say we have one of these at the school. We have basically a cube that's made out of metal, but it's this kind of loose metal. It's almost like a screen. Okay, it kind of has the texture of like a screen door. So it's kind of like this. You've got like a bunch of like grids, okay, and it's made out of metal. Okay, so Faraday called this a Faraday cage. So you have this metal cage, which is known as a Faraday cage. And the reason why is because Faraday figured out that if you're standing inside of a cage like this, right? If, for example, someone were to come along and apply any kind of electricity to the outside of this, you would not get shocked. You would be totally safe inside of here, basically. And you can extend that to the extreme, which would be like, suppose that lightning struck the cage. Lightning is a massive flow of charges, right? What ends up happening is that lightning basically just goes all along the edges and straight into the ground. Almost following the path of least resistance in a way, because electricity flows really well through metals, right? It doesn't flow very well through air. So this cage basically protects the lightning from getting directly to you. So this is why people say that if you're in a thunderstorm and you have nowhere to hide, if you stay inside of your car, you should be safe. Even if your car gets struck with electricity, with a lightning bolt, the lightning basically goes straight into the ground, and you will be totally safe inside. Now, it doesn't work if the cage is made out of plastic, because then it might actually go directly to you, the lightning. But as long as it's made out of metal, you're totally safe. Does that make sense?
Mm-hmm. Oh, what if you... I've also heard, like, maybe... What if you take off your shoes? Does that, like, increase, like, if you do get struck by lightning? Like, you'll be grounded, and, like, the charge will go through you? I mean, you'll probably be hurt.
So if it's a direct lightning strike, it's still going to be really painful, probably. Doesn't mean it would kill you, but, yeah, your point is that if you're wearing, like, rubber shoes that are really dry, and if you get struck by lightning, then that might be more dangerous than if you weren't wearing the rubber shoes, because you would just absorb all that extra charge instead of having it flow through to the ground. I don't actually know the answer to that question. I just know when we're handling things with electricity in the lab, it's a good thing to have your feet with, like, wearing rubber soles. Because I would think that what you'd be doing if you took off your shoes is you'd be creating a better path for the electricity. You know what I mean? Whereas if you're wearing the rubber shoes, the electricity may just go straight to the ground instead of to you. Does that make any sense? It's like, I think without your shoes on, you'd be more like a lightning rod. You know? I think so.
Mm-hmm.
You know what
Makes
I mean?
sense.
Because I think our bodies certainly have more conductivity for electricity than the air does, right? Because we're filled with water. And I know when our bodies get wet, the electrical resistance to for our bodies, when we get wet, can reduce by a factor of like 1,000 or something like that. This is why it's really dangerous to like get into a bathtub and handle any kind of electronic device, is because when your body's wet, it's a lot easier to become electrocuted. Whereas when your body's dry, it's a lot harder. So you'd never want to like dry your hair in the shower, obviously, right? That's not something I need to tell you. I think everybody knows that. But that's the reason why, is because your body basically turns into a conductor when your body's wet, you know. Whereas when it's dry, we have very, very low resistance. So I don't know if I'm right about that, Cam. I'd highly encourage you to maybe read some more about it. Maybe I can read some more too. Shouldn't be too hard to find some information about that. Like,
Mm-hmm.
should you wear? But I think you'd want to be wearing shoes that were insulated to prevent the path from being there. Because if you think about the Faraday cage, the reason why it works is because the electrical charges, well, first of all, they tend to just go to the surface, right? That's the idea of like what number 2 says. Number 1 also applies to this. The electric field inside of the cage would never get above 0 because the cage acts as a conductor, right? This is something that I could show you in the lab. What we do is, instead of having a person inside of here, you put an electroscope inside of the cage, and then I take this device that creates static shocks and just basically run it all over the cage, and you'll see all these electrical sparks that shock the cage. But the electroscope never does anything, which is kind of a proof of number 1.
Cool.
Okay, so let's keep going. So number 3 says the electric field at a point just outside a charged conductor is perpendicular to the surface and has a magnitude of sigma over epsilon naught, where sigma is the surface charge density at that point. Okay, So let's just do a quick Gauss's law thing here to prove this. So in order to do this, what we do is we say, suppose that I take a Gaussian surface, right? And I situate it right here on the edge of my surface like this. So it's small enough so that I could say that near this surface, the electric field lines are going to kind of point this way. And I basically am going to use another pillbox, or which is really just a cylinder here. And we'll say the cylinder, is half of it's inside and half of it's outside, okay? Now, the interesting thing that happens here is that now the electric field on this side is 0, but the electric field on this side is something that we're going to call E, and we want to solve for what that is. If the surface charge density is sigma, then what we can say is that the left-hand side of Gauss's law's equation is going to become E times A, where A is going to be the area of that cap. The right-hand side of the equation is just going to be sigma times A over epsilon naught. This is exactly like the last problem, except there's not a 2 over here, because there's no flux on the bottom portion. Oh, DeHouse says, but the metal part of the car doesn't touch the ground, right? Yeah, but it's low enough to the ground, and there's also metal in the tires and stuff like that. Not in the tires, but in the axles of the tires. So it's close enough that it can still jump to the ground, DeHow. Not to mention that if you're in a thunderstorm, the wheels are going to be wet, so there's going to be like water flowing over them. So I'm pretty sure that the electricity can flow through that pretty well too. All right, so in this case, we end up getting these cancel, and we get that the size of the electric field is just sigma over epsilon naught near the surface. Okay. Now the part I didn't mention about this is I have to prove that it's perpendicular too. So in order to prove that it's perpendicular, I should have done this part first really. What we say is, okay, suppose I've got an object, it has excess charge. We know from the first two that the charge all has to go to the surface and the electric field inside is 0. And now we say, what's the direction of the electric field on the surface? So one possibility is that the electric field is going to be perpendicular and pointing this way. And it's possible that there would be some component of the electric field that might point tangent to the surface like this. Maybe call it E parallel. But if there was, the effect would be that that would cause this charge to want to move to the right. So if you have any type of a electric field that is not just perpendicular, it's going to tend to cause your charges to basically move around the edge, which means that the system will no longer be in equilibrium, right? So that means that you can't possibly have a parallel component, and all of the electric field has to be just perpendicular to the surface. Okay, so now we know for a metal object, all the charges on the surface, the electric field inside is 0, and the electric field is perpendicular, and we also know what the size of that electric field is. The size of the electric field is going to depend on sigma, though, and that's what the fourth part is about. The fourth part says, on an irregularly shaped conductor, the surface charge density is greatest at locations where the radius of the curvature of the surface is the smallest. I can prove this for you when we get to the next chapter, but what I can tell you now is just kind of what it generally means. Okay, so it says, on an irregularly shaped conductor, the surface charge density is greatest at locations where the radius of curvature is the smallest. Radius of curvature is a measure, if you don't know what it is, it's a measure of how curvy something is, okay? So I'm going to take an object that is kind of widely curved on most of its parts, but we're going to have it come down to a very sharp point right here, like that, okay? So we have some piece of metal, and we say that it contains charges. What number 4 is telling us is that the surface charge density is the greatest at locations where the radius of curvature is smallest. So what that means is that the charges are going to tend to spread themselves out in regions where the curvature is low. But when the curvature gets really high, like in these regions right here, this is where the charges are going to pile up a lot, basically. So what you're going to find is that sigma is greatest right here. That is to say that you get the most charges per unit area right here where this point is. Now, if we combine this with what we learned in the last part, which is that the size of the electric field is related to the surface charge density, understanding that the surface charge density is small over here, and it's big over here, it's not a constant, okay? Not a constant. Then which point would have a bigger electric field?
The less curvature.
Yeah, so the electric...
Rated.
Yeah, so over here, right?
Mm-hmm.
The electric field is biggest over here. Now, there's another piece of this that should be pretty obvious to you. If you want to shock somebody, you know that you can basically scuff your feet on the. You can take like if you're wearing socks or something, you have like some nice like shaggy carpet. You can rub your feet on the floor, and that will develop a charge on your body, and then you can go and shock people, right? But if you want to shock someone, you probably don't shock them with the palm of your hand, right? If you want to shock them, you usually like use your finger, right? Because your finger is like the pointiest part of your hand, right? That's the place where the surface charge density is going to be greatest, where the electric field is the biggest, and the place where the electric field is the biggest is going to be the place where you can more easily generate a shock, like a static shock. Because the static shock is only going to occur when the electric field becomes big enough to kind of cut through the air, so to speak. To cut through the braking strength of the air and create that spark. Okay. So I'll prove this number 4 when we get to the next chapter. We can't truly prove it now. I can just describe to you what it means. And those are the 4 rules for conductors in electrostatic equilibrium. And they are things that you just kind of need to know. You just need to remember these things as they will be showing up quite a bit from time to time. Every once in a while, I'm just going to refer back to these. You know, I'll be like, oh, but we know that the electric field inside has to be 0, and we can use that to prove other things, or, you know, any of these things. So these will be kind of some principles that we can apply in problems, and we will immediately do that in the problem that we're going to do now. Prince Ali asked, does the tire grip have anything to do with... Oh, man, I just realized that this whole thing right here was blocked off because I moved where the chat was. I'm sorry for that. Okay, so your question was, does tire grip have anything to do with charges? I don't know. What do you all think? Does it?
Tire grip.
I would say all forces have something to do with charges. Almost all forces. And the friction force is no different.
Oh, like yeah. Oh, is that what he's talking about? The friction?
I think so. Yeah, grip is friction, right? Yeah, it totally does. You know, if I take my hands and I try to push them through each other, I can't, right? That's a stupid thing to say, but you know it's impossible to like push my hands through each other. But if you ask why, you might say, oh, well, there's a contact force between my palm and my other palm, and you know, it's just like it's a force. What kind of force is it? Well, I guess it's like a normal force. Then you ask like, well, what is that? Well, really, what it is like there's electrons in my hands, and I get them close enough together, and I can't push through them. That's at the core. That's what's happening basically. Negative charge, negative charge. I can't overcome it basically.
Is there a measure of slickness? If you know what I mean by that.
Yeah, friction. Yeah, is the measure of slickness, right?
Okay. Yeah, I mean, yeah.
Yeah. From really sticky down to the, you know, frictionless things that we talk about in physics that aren't truly frictionless, but just have a really small coefficient. Okay.
Would it be dimensionless?
It is. Yeah.
Mm-hmm.
Okay, I want to do this problem, and like we could take a break and then come back and do this problem. I'm just gonna leave it to you all what you want to do. Do you want to take a break and then come back and solve this, and then we'll be done, or do you want to just keep going until we're finished? We'll have just a little bit longer lecture today.
I'm good keeping going.
Yeah, we can just.
Yeah.